Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh. Today we want to present about conduction graphical analysis on heat transfer for subject EMMH 3553 heat transfer. We are from BMMB S2/1. This is our team members. First is me. My name is Atika binti Abdul GHANI. My matric number is B0920100047. Second is NURHANANI binti ZAINAL ABIDIN. The matric number is B09201002X7. Third is SABRINA binti Abdul WAHID. The matric number is B0920100367. Fourth is NONNY anak UMPING. The matric number is B0920100166. The last is NURULHUSNA binti Muhammad AZHAR. The matric number is B0920100152. This is our introduction. First, I want to present about objective. The objective are to create two different field surface according to our creativity using suitable design software. Second is to show the temperature distribution along the heat transfer surface field in free and forced convection. Third is to perform heat transfer simulation using suitable software on a thin surface. What is conduction of heat transfer? Conduction of heat transfer is the transfer of heat by means of molecular excitement within a material without bulk motion of matter. Conduction heat transfer in gases and liquid is due to the collision and diffusion of the molecule during their random motion. What is the heat sink? Heat sink is the component that transfers the heat from any device to the cool side and prevent overheating. The heat is carried from the bottom or base of the structure and through conduction and carry the heat to the cool side and perform heat transfer. Heat sink is required on many devices such as CPU. The CPU without the heat sink will be overheated and burned, so heat sink is one of the most important components to absorb heat from it. What is thin surface? Thin surface is surface that extends from an object to increase the rate of heat transfer to or form the environment by increasing convection. The amount of conduction, convection or radiation of an object determines the amount of heat in transfer. We have three types of fin. First is straight fin, second is fine fin, and third is annular fin. Application used for this assignment is SolidWorks software.
Assalamualaikum warahmatullahi wabarakatuh. My name is NURHANANI binti ZAINAL ABIDIN. So I will present my part for design 1. This is my design 1. It is like triangular shape with the material of aluminium bronze. The ambient temperature is that I choose is 30. The fin base size is 40 times 40. Convection coefficient is 5.03. Average heat flux 1500. Temperature on cold side is 349.75 Kelvin. Temperature on hot side is 370.45 Kelvin. So this is the dimension of our design line. So you can see the thickness, the total thickness of from fins to base is 7 mm. The thickness of each of the fin is 0.5 mm. Thickness of the base is 1 mm. The length and the width is 40 times 40. After I apply heat power 166.549 watt and convection 5.03 on the body, you can see that the base of the base is on hotter side, that is in red shaded, and on top of the fin is blue shaded, which is the colder side. So the max temperature is 4.284 to the times 10 to the power of 3, and minimum is 4.209 times 10 to the power of 3. The mass density is 7,400. The thermal expansion coefficient is 1.7 times 10 to the power of -5, and the thermal conductivity is 56. The specific heat of this plate is 380 joule per kilogram Kelvin. I think that's it from me. Thank you.
My name is SABRINA binti Abdul WAHID. My MATRIKS number B0920100367. So I will continue to present about design 2. The criteria for design 2 is ambient temperature Celsius is 30, and we use the fin space sizes is 40 mm times 40 mm. Average heat flux on the cool side 1500. Average temperature on the cool side 76.6 Celsius or 349.75 Kelvin. Average temperature on the hot side 97.3 Celsius or 370.45 Kelvin. Convection coefficient is we use 5.03. Next, the dimension of design 2 is the base is 40 times 40 and the thickness for curve for the fin is 1 and the base also 1. The radius for the curve is 1.5. The distance of fins to the base is 7.31. Okay, so this is the simulation for design 2. We get the maximum temperature Kelvin 3.883, minimum temperature 3.812, mass density 7,400 kg per meter cube, thermal expansion coefficient 1.7, thermal conductivity 56 watt, specific heat 380 joule. So we use the SolidWorks to find the simulation, and from the simulation we have to get the heat power and convection, and the material we use is aluminium bronze. So to get the heat power, my member have to find it at the discussion. So that's it for me.
Sejahtera, I'm NONNY and UMPING, and I will explain about the discussion. Okay, discussion number 1, feed efficiency. Okay, feed efficiency can be calculated by using a formula where feed efficiency equal to actual heat transfer rate from the feed divided by ideal heat transfer rate from the feed if the entire feed were at best temperature, means that feed efficiency equal to Q feed divided by Q feed maximum. Okay, for our information, fin tips usually exposed to surroundings, so that the proper boundary condition for the fin tips is convection with the effect of radiation. The temperature of the fin will drop along the fin, and the heat transfer from fin will be less because of the decreasing temperature difference toward the fin tip. Temperature difference is the subtraction of the surface temperature with surrounding temperature. The next slide is fin effectiveness. As we know, fins is used to enhance the heat transfer, but there is no assurance that adding fins on a surface will enhance heat transfer. The use of fins on a surface cannot be recommended unless the enhancement in heat transfer justifies the added cost and complexity associated with the fins. Okay, the performance of fins expressed in terms of the fin effectiveness. Okay, here is the formula for the fin effectiveness, where fin effectiveness is equal to heat transfer with fin divided by heat transfer without fin. Heat transfer without fin is also equal to the convection heat transfer, where the formula for convection heat transfer is equal to heat transfer coefficient multiplied with surface area multiplied with the temperature difference. So the final formula for the fin effectiveness is equal to heat transfer with fin divided with the convection heat transfer multiplied with the surface area and multiplied with the temperature difference. Next is the comparison between design 1 and design 2. Okay, as we can see here, there is no quite difference between design 1 and design 2. It's just that the difference happened to the maximum temperature and minimum temperature. Okay, for maximum temperature, design 1 is 4.284 multiplied 10 to the power of 3. Okay, for design 2 is 3.883 multiplied 10 to the power of 3. Okay, here the design with the greater maximum temperature is design 1. Okay, for minimum temperature, design 1 is 4.209 multiplied 10 to the power of 3, and design 2 is 3.812 multiplied 10 to the power of 3. So, the design with the greater minimum temperature is design 1. Okay, for the other properties, design 1 and design 2, there is no difference. With the mass density, thermal expansion coefficient, thermal conductivity, and specific heat. This is because the two design is made from the same material, which is aluminium bronze.
Assalamualaikum, I'm NURULHUSNA binti AZHAR. My part in this presentation is conclusion. Finally, we look at heat transfer conduction graphical analysis using two alternative design, design 1 and design 2, with varied amount of fins. We may deduce from a simulation that design 1 has a higher temperature with maximum temperature of 4.284 exponent power of 3 and a minimum temperature of 4.209 exponent power of 3. Meanwhile, when compared to design 2, the maximum temperature is 3.883 exponent power of 3 and the minimum temperature is 3.812 exponent power of 3. It is because design 2 has a larger number of fins, so it can remove more heat. To get a lower temperature, we can also increase the length and surface area. Furthermore, when the distance between the fin is small, the heat evacuation is high. As a result, the rate of heat transfer can be differentiated by the number of fins used.